My name's Nick, for those of you who haven't met me. I'm currently a postdoc at the University of Washington, starting a faculty position at Amherst College in the fall. And I'm going to be the session chair for our first afternoon session focused on observations of the subglacial environment. So, our first talk is by Eliza Dawson, who's going to tell us about integrating models and radar data. And as always, we'll have 10 minutes and I'll stand up at 8.
Hi, I am a student working in the Stanford radio Glaciology group, and the work I'm going to be presenting is both with the radio Glaciology group and also work I've done with Lamont-Doherty at JPL. So please judge me. So for the next 10 minutes, I'd like to direct your attention to conditions at the bed of the ice sheet. And in particular, I'd like to explore the question, how does ice sheet flow depend on the basal temperature regime? Temperature controls the flow of ice sheets through two key feedbacks. One is the runaway increase of internal temperature and deformation rate. So as temperature increases, we get velocity increases, viscosity is going to decrease, and we're going to get higher deformation rates. The second mechanism, and the one I'd like to focus on today, is the thermally regulated activation of sliding. And after we have the onset of sliding, thermomechanical feedback can exist in regions where there's increased energy or increased dissipation of energy. And in these regions, it can then trigger a feedback on the thermal state. This feedback is much more complex, and there's a lot of new research in this area, and it's currently missing in ice sheet models. So let's zoom in now to this region right here, where the sliding begins. And we know that below this, where the temperature is below the pressure melting point, the bed is frozen, and there's no sliding. At pressure melting point, you have a thawed bed, and there's sliding, which depends on basal friction, among other things. Often, it's assumed that there's a hard switch and onset of sliding. However, this causes the rapid downdraw of ice and refreezing of the bed as soon as sliding onset begins, which is a problem for ice sheet models. Instead, I'd like to assume that there's a subtemperate region, which is follow-on work from Fowler, and Mintelli has done some new work on this. And in this region, sliding depends on friction, but also what's very important is temperature. And here, the sliding velocity is constrained by the need to maintain the energy balance. So basal conditions vary broadly across Antarctica, from the interior where the bed is frozen to fast-flowing ice sheet margins, which really motivates the question, how does ice flow depend on the basal temperature conditions? So we know that both temperature and the basal drag are important, but in what way? Here I have filtered the surface velocity into two groups. One is for regions that are flowing very fast, which is, you can see, is primarily highlighting the ice streams, and this area is safe to assume that is thawed at the bed. I also have a filter for very cold interior regions where the velocity is less than 5 meters per year, and the bed is probably dominantly frozen. And if I plot the histograms of basal friction coefficient, what we can see is that these fall into two separate distributions. And in particular, we can see that these fast-flowing thawed regions have friction that is lower than frozen areas. And I want you to note that the mean thawed friction is around 40. So remember that, we'll be using it in future slides. So what would this kind of propagation look like if we allow this frozen to thawed transition to occur? We're going to get increased area at the pressure melting point. We're going to get a decrease in basal drag as the more of the bed becomes thawed. And what's interesting is we're going to get an evolution in the surface profile. So when the bed is all at the pressure melting point, we'd expect a more elongated, lower surface profile. This is like an ice stream, right? If the bed is totally frozen, you get a steeper surface slope, and it's much thicker ice. Think like the interior of the continent where it's very frozen. Okay, so now let's zoom into the Thwaites and Pine Island region. Here we're looking at the basal melt rate, and in gray you can see areas of the bed that are frozen. And there's some interesting sections between Pine Island and Thwaites Glacier. In particular, I'd like to point out this frozen patch right near the southwest tributary of Pine Island, and also there's a strong temperature gradient here along the eastern shear margin of Thwaites Glacier. And both these regions are interesting for learning about what sorts of cross-glacier interactions there could be between the two catchment basins. So if now we're looking at just the Thwaites Glacier domain, and radar provides some very interesting observational evidence of potentially a strong temperature gradient along the shear margin. So the eastern shear margin is not constrained by bed topography or strong bed geological features. But what we do see from radar is two separate camps of the bed reflectivity values. And one thing that can result in these values is a temperature transition. And on the right, you can see the surface velocity from ISSM. You can see the shear margin here, and also basal temperature values. So I would like to now look at what would happen if we simulate a basal temperature transition in ISSM. And I will be showing you ISSM results using BedMap2, Reno 2017 velocity. The surface mass balance is from LeBrock 2010, and I'm using Shapiro geothermal heat flux. The horizontal resolution is an adaptive mesh, and so areas that are flowing very fast, I have a resolution of about 600 meters. Where I have fast, much slower flowing, the maximum resolution is 20 kilometers. And the experiment will be a transient model. First, I'll show a little bit of model relaxation, and then I will induce a step change where I've reduced the basal friction and show some initial results in how that evolves. So here we're looking at basal friction coefficient from my ISSM simulation. This is just the inferred value that comes right out of the model. Here I have taken all the regions within 3 degrees of the pressure melting point and prescribed a friction coefficient that's equal to the mean thaw value of 40. And so basically what this is simulating is what would happen if we take this subtemperate region, this region that the sliding depends on the temperature, and thaw it. Okay, so here on the x-axis we have time in years. The first 10 years is just allowing the model to relax, and then we can see this step change prescribed. And for both volume and surface height, these next 10 years, we can see decreases in both the surface height and volume after we've reduced the friction. Here we're looking at velocity, and we can see here initial velocity. This is after the step change has been prescribed. This is year 20. And now here's the change. And the eastern shear margin really gets highlighted as both increasing in velocity and also shear margin moving further out. So it's kind of migrating. So I think I've kind of set good motivation that the temperature conditions really matter. In the future, I'd like to expand the model domain and also increase my runs for a lot longer. The velocity is constrained on the border of this current domain, so that limits the ability to capture the shear margin. I'd also like to experiment with different sliding laws to capture kind of this spread in thermal propagation and try to understand better how sensitive is the model to the sliding law and this temperature role. And I'd also like to work on defining the model definition of the subtemperate zone and working on how to parameterize this value. I'll leave you now with a couple of key takeaways. Basal sliding depends on temperature, and the subtemperate region is important for the thaw propagation. Also, friction at the bed falls into two different camps, one for frozen regions and one for thawed regions. And importantly, models and observations show weights and probably many other parts of Antarctica, which I'll be looking at in the future, may be significantly controlled by the thermal state, which could drive retreat and contribute to sea level rise.
Thanks, Eliza. As we transition, we probably have time for a quick question. Okay, we'll save them for the discussion. Next in this session, we have Brad Rosenheim, who's going to be telling us about observations from subglacial Lake Mercer.
Starting in the middle there. Okay, thanks everybody. Thanks to the conveners. I'm going to take us back to Lake Mercer for the SALSA project and sort of highlight some of the interdisciplinary work that we're doing from a carbon perspective. And this is going to pretty much do some due diligence to Ryan's interpretations of ages that she presented earlier in the morning. So here's our team again. Fantastic science team, all pictured, most of whom are all pictured here. And there are the authors that contributed directly to this presentation. Of course, they did all the good things, and any mistakes are mine. So here's the drainage of the dual drainages of Lake Mercer, which is shown here. And there's our nice acronym title that was running concurrently with Tabasco, as we found out. But the subtitle is what's important to this talk, and it's that we're performing an integrated study of carbon cycling in a hydrologically active subglacial environment. And so what I want to do is present our results from Lake Mercer here, which was last field season, and I want to put them in the context of the WIZARD project, which visited Willans, as well as some of the previous work along the Central Coast. So to do that, I want to start with this plot that's in the supplemental material of the Kingsley et al. Paper, and I want to spend a minute or two on this because it took me a minute or two to realize what this was about. But this is this is a really nice plot, and it's buried in the supplemental information. But this is what we measure with radiocarbon, right? It's an isotope ratio of 14 to 12, and these are the measurements from 11 different samples that were chosen from previous work as well as the WIZARD project. And if you follow the decay curves up, you're making an interpretation, right? When you get to the intersection of fraction minor of 1, which was the 14 to 12 ratio of the atmosphere in 1950, you can interpret that as the age, so long as your carbon was formed by a process and unadulterated during its travel along this curve in time. Okay, so these were 11 different radiocarbon dates interpreted this way from Kingsley and Shearer et al. Paper last year. And then, of course, from the grounding zone, they measured amphipods, right, which were quite a bit younger. Right? We moved all the way up this axis. If we follow the decay curve, this translates to an age of about 1,000 to 1,300 years old, which is typically the age of the marine reservoir in the Ross Sea and elsewhere around Antarctica. So a big difference here between what was living and what was in the sediment reservoir along the Central Coast before the WIZARD project. All right, so bear that in mind. We're going to come back to this diagram. So here we are in Lake Mercer. This is our borehole. We equilibrated to within 101 meters of the ice surface. This is our borehole, and down here is our lake. Looks skinny compared to the 1,092 meters of ice that we bored through, but it was a 15-meter deep lake. It's a pretty significant lake, about 2 times the size of Manhattan. Okay, so if we want to think about a lake or an aquatic ecosystem, and sorry for this diagram, but if we just focus, if we just ignore the lines and arrows for now, it's a pretty simple carbon diagram. We have a pool of oxidized inorganic carbon, dissolved carbon. That's sort of the source that can be run through these machines here, autotrophs and heterotrophs, and form organic matter, which ultimately, through the process of sinking, what doesn't get re-eaten will end up in our sedimentary organic reservoir. And there's a lot of different arrows that can short-circuit this in some different ways. And in the end, we can end up with a smaller dissolved organic carbon pool up here. Now, this being a subglacial lake, right, we would not expect to see photosynthesis, and we didn't know of any volcanic activity or anything like that. So we wouldn't expect to see chemosynthesis either. And that leaves one sort of route for primary production, and that's chemolithoautotrophy. Or simply, you could have a system where we only have heterotrophic biomass. So what did we find in Lake Mercer? Well, from the bottom up, we found sediments, and this is the CT scan at the fabulous new Corvallis core repository of our multi-core, showing the laminated sediment on the top, and we're slicing through the core and seeing the diamecture on the bottom. And going into this project, and based on some of the work that was done at Willans, we thought that this would be about, it would be very old. There'd be very little radiocarbon in the sediment. So we sort of hypothesized 37,500 years based on some ages that were unpublished at that time. And in the water column, well, we found biology doing things. And I think I can get away in this crowd by saying those green dots are life. Those lines in there are life, and we can move on. Right? We'll make you ride up here and explain what that means. But this is Mark wants, Skids wants me to go. So these are actually observed out in the field. These are live cells. They took the stain, microbial scale. I forget what that scale bar is. But this is a picture from WAIS. And this is work by graduate student at University of Florida, Christina Davis, which found culturable microbes as well, and that's why these lines form in the petri dish. But Christina's work has really focused in on this process here, which is the oxidation of ammonia. So ammonia oxidizing bacteria and archaea seem to be one of the role players in this ecosystem. All right. So now we want to get into how does that affect our interpretation of these radiocarbon ages. And to do that, we have to really get into the rates, which apply to the arrows in that diagram that I showed earlier. So this is Tristy Vic Major's work and WAIS work. What they've done is they've looked at C14 bicarbonate uptake and leucine uptake. So this is primary productivity. This is heterotrophic production or consumption, simulatory consumption. And you see that there are rates in these blue lines. These are the live cultures, and we see rates that are about primary productivity rates that are about an order of magnitude higher than the heterotrophy. But there's rates nonetheless. So what's interesting to us in trying to interpret these sediments is that in the water column, primary productivity is about a little over three times the amount of activity as there is in heterotrophic productivity. But at the interface between the soils and the sediment, you sort of see the opposite. It's about 2.5 times more productivity happening due to heterotrophy of the sediment-water interface. So this is pretty neat. So what do we find in terms of radiocarbon? We're going to sew this all together here. Now this is using the Ramp-Pyrox method. Most of these gray lines from the Kingslake et al. Paper were done using the bulk gauge, which is a mixture of different sources of carbon. And using the Ramp-Pyrox method, we can simplify that mixture, and also we get an idea of what the other end member is, the old end member. So these red lines show sort of the youngest and oldest Ramp-Pyrox splits from Ryan's work. And you can see that we do get this to be younger than what we had thought from the previous work along the cyclocosins and wizard. And also of value, we see that there's a very old end member, probably dead in some cases. We see actually limited ages where we can't even detect radiocarbon. Comprehensively, we measured the DIC of the lake water, and we come up with an older age there too. So this blue line. We measured pore water, and that's a high uncertainty on this because of all the dilution steps and everything. That's older. So the important part is that everything we're measuring is older than the organic matter in this system. So where does it come from? Ryan discussed earlier that in this sort of plot, this suggests that the organic matter, not necessarily sediments, but the organic matter in here is marine origin by the stable isotopes and the carbon to nitrogen ratio. if we go back to this diagram, and now I've added some sizes of these reservoirs based on our work here, to think that the processes here are converting DIC and putting it into sedimentary organic matter is sort of looking at it as the tail wagging the dog. Okay, and that's not really happening. This reservoir is about 2 times as big as that reservoir, and the rates of production here, it would take about 10 to the 30th years to use all of the DIC up and make it into organic matter, and that's not even including the filled drain cycles of the lake. That's just taking one static lake volume. Okay, so virtually no radiocarbon in the DIC in the pore water. There's some radiocarbon in the sedimentary organic matter. Radiocarbon years of age is about 17,000, 20,000 years old, so that's really interesting. And basically this C14 in the sedimentary organic matter is not controlled by the lake processes. It's here, it was introduced to the system by a different process. Okay, so here's a sort of a summary diagram that Ryan has made. We're incorporating this carbon cycle into our cutaway diagram. And basically, we have to consider the dynamics of this during or since the LGM. So, at that, I would like to advertise Mark Skidmore's poster on more water geochemistry. Tim Campbell is Mark's student. He's got a sediment poster, and we have one more salsa talk coming up by Chloe Gustafson.
As we transition, any quick question for Brad?
What do you think about the sediment age? Why do you think it's 17,000 years old, not radioprimitive?
So what do we think about the 17,000-year-old sediment age? Well, given that it's marine in nature, by the other isotopic parameters, the working hypothesis is that is marine carbon that is made in there. Now, one thing that I talked to Reed about, we have Dave Harwood here and Amy Leventer have not seen any age diagnostic diatoms. We've seen very few diatoms in the sediment. So, but we didn't see them at the grounding zone either. Right? So it doesn't have to be the diatoms don't have to be there to be to make it a characteristic of marine organic.
Yeah, diatoms would mean that there was no ice shelf.
Right.
You could have marine organic carbon without underneath that.
Exactly.
Great. So next we have Grace Barcheck, who's going to tell us about the progression of seismicity at Lamont-Doherty Street. Grace.
Thank you, Nick. Okay, hi everyone. My name is Grace Barcheck. I'm going to be revisiting an old friend, the Willans Ice Plain Stick Slip Cycle. I've heard about it in a while. And we're going to use some new GPS data to sort of reevaluate the relationship of the stick slip cycle to the tides beneath the Ross Ice Shelf. Which one is the laser pointer? The green one. Yes. Okay, so the region we're looking at is the Willans Ice Plain, which I guess at this meeting will just be known as the region downstream of Lake Mercer, which is like right there. It's this big, wide, flat place where the Willans and the Mercer Ice Stream come together. And it's bounded on 2 sides by grounding zones and 1 side by a shear margin. And what's interesting about it is that if you place a GPS out in the middle of the ice plain and you look at the displacement through time, it moves in these sudden surge events that happen once or twice every single day and results in the ice moving about half a meter in 30 minutes. So these unstable slip events are an interesting characteristic of this particular region. And there's been a whole bunch of work done on the stick slip cycle over the last couple of decades, but I'm just going to point out a couple of the previous observations and sort of reevaluate them given some new data that we have. So previously it was determined that the timing of those unstable slip events is modulated by the tides beneath the Ross Ice Shelf. And in previous work, for the most part, people used either a GPS, so sort of downstream on the floating part of the Ross Ice Shelf somewhere, or the CATS tidal model for the most part. And if you use that data, it looks like there's 1 slip event per sort of tidal cycle, usually at the high tide time of tidal cycle, and then again at the low tide, sometime around low tide. So you get sort of like high tide event and a low tide event. And the timing of those was thought to result from the interaction between the sort of constant upstream driving, loading, and downstream time varying loading. And I'm going to suggest that maybe one tide per day is not exactly the right forcing, and sort of reevaluate what controls this tidal modulation. The other thing is that the unstable slip events, they're kind of like earthquakes, right? And so just like an earthquake, we can figure out where the high-speed phase of unstable slip begins. And there are two of these epicenters of unstable slips. So these are like the epicenters of earthquakes. And Pratt et al. In 2014 suggested that there's two of them. And so one unstable slip event will start at either one or the other. And usually the central epicenter, which is this red star, is where slip begins at high tide, and the yellow one is where slip begins at low tide in the previous work. And what's kind of interesting about this, these two epicenters, you can actually distinguish which one the slip starts at by looking at far field seismic waves recorded in the dry valleys, thousands of kilometers away. So for two slip events in early 2014, we have downstream displacement and far field seismic wave radiation for 2 hours around the event. And the first one has 2 pulses of seismic wave radiation, and the second one has 3. And so Pratt et al. Suggested that if that first pulse is absent, slip starts at the central epicenter, and if the first pulse is there, slip starts at the grounding zone. So we have a little far field diagnostic of where unstable slip started. But it's not really known why. Why are there 2? Why did they switch back and forth? So maybe we'll get some constraints on that today. So the data set that I will be presenting is 3 GPS. One is near each of these 2 epicenters, so the blue and the orange are these 2 GPS on grounded ice, next to the locations where high-speed slip starts. And the green one is on floating or nearly floating ice, just across the grounding line from this grounding zone epicenter. And this is cool because it allows me to look in great detail at each unstable slip event and how it relates to the tides down here right next to that grounding zone epicenter, and not some region like down here somewhere. So first off, this is the tidal model that a lot of the previous work has been done using. And it has 1 tide per day, and then this is data from that GPS that's on floating ice. And some of the days have about 1 cycle of tide per day. Most of them actually have 2. So that's kind of a new observation that might change how we think about the slip events being triggered. They don't have the full range and amplitude of tide, but there's definitely 2 periods of falling and rising tide in those days. So is 1 tide per day the correct forcing? Maybe not. I definitely see 2. The other thing that I noticed in this data set is that there is very, very, very often a little period of precursoring motion before the unstable slip event, primarily at this grounding zone location. So here is downstream displacement at the central GPS, differentiated to velocity. This is like what a slip event usually looks like. And then if I add the orange one, here's this little short, like 7-minute little blip of displacement that I'm calling a precursory sliding. And so this is incredibly common in this data set. And so what I do, I have 75 slip events in this data set, and I categorize them based on whether they have a short duration little precursor, so that one's like 7 minutes long. This one is like an hour and a half long, maybe, and sometimes there's none at all. So I categorize each slip event by how long the precursor is and how long or whether it exists. And then I plot the timing of all of the slip events as a function of the salient features of the tides at that GPS by the grounding zone epicenter. And so we have tidal height, so amplitude, the vertical velocity, and hours since the previous high or low tide. So that's hours since the previous inflection point. And you can see that the slip events start at a whole range of tidal heights, but almost all of them actually occur during falling tide once we realize that there's actually 2 tides in the location. More than 80% of the data set is actually during a period of falling tide. So this is probably an important aspect of the tidal modulation of the timing of these events. And so now I would like to just draw your attention to the orange and red triangles, which represent all the slip events that have any kind of precursor at that grounding zone GPS, so the one that's next to the floating ice. And so the orange ones and the red ones, and we'll just look at this lower figure over here. The orange ones and the red ones are almost all occurring during a falling tide as well. So there's a pretty strong correlation between falling tidal phase and some kind of precursory motion before the slip event at that grounding zone location. So that's kind of interesting that falling tide encourages like some kind of slow slip event and not actually the full unstable slip. And finally, if we go back to that observation I showed you at the beginning, where the if that first phase of seismic wave radiation is observed in the far field, we know that the slip started at the grounding zone. And so that's represented over here by gray circles. So, and you might notice that there's a few gray circles on here, but almost none of them are actually around these orange triangles. So what that means is that in the presence of this short duration precursor at the grounding zone, there is no seismic wave radiation from that region, and that means that the unstable slip actually starts at the other epicenter. So the short duration precursor, not the long one, interestingly, but the short duration one actually relieves some amount of stress by the grounding line and like sends the slip event to start at the other epicenter. Okay, so why does the epicenter location switch? Well, maybe it's something related to these short duration precursory movement events before the unstable slip events. Okay, this is my last slide. So I have hopefully shown you that there are actually usually, not always, but usually 2 cycles of tides per day at that grounding zone location where unstable slip starts. And that actually most of the slip events actually have a little bit of precursory movement at the grounding zone before each one. And that precursory motion is largely triggered by falling tides. And that when that happens, when there's some kind of precursory movement triggered by falling tides, it relieves stress at the grounding zone and sends unstable slip to start at the other epicenter. So this is kind of a summary. The occurrence of a period of falling tide triggered slow precursory motion near the grounding zone epicenter affects when and where unstable slip events begin. So that's all. Thank you.
Thanks, Grace. Any quick questions for Grace as we transition? Yeah, super quick.
Are you aware that the Ross has got video of the full slip event? We have the camera, downward-looking camera running all day long, and it was sitting there, and all of a sudden, at the grounding.
I was not aware of that.
We've got a video of the slip event initiation and ending.
That's cool. Yeah.
So get in touch with Ross.
Okay. Yeah, thanks.
Thanks. So, for the final 2 talks of the session, we're switching to electromagnetic methods, and Chloe Gustafson is going to tell us about some measurements taken over subglacial lake moments. Thanks, Chloe.
Hi, I'm Chloe. I'm a 5th year PhD student at Lamont right now, and the work I will be sharing is work I've done with my advisor Carrie Key, Matt Siegfried, and Helen Fricker. So to start off, I'm going to break down sort of the 3 aspects of my title: basal to bedrock, magnetotelluric imaging, and an active subglacial hydrologic system. And spoiler, we're sticking in the Willans ice plain. So to start, here's our general schematic of an ice sheet flowing off of the continent and into the ocean. Sorry, this is blurry. That's okay. Okay. So when I'm thinking about basal processes that I'm interested in, it's the hydrologic systems that we know exist at the base of the ice sheet thanks to satellites like ICESat and other remote sensing methods. So we know that there are lakes that actively drain and fill on monthly to yearly timescales, and these lakes eventually transport water into the Southern Ocean beneath the ice shelf. So I'm very interested in these sorts of basal processes. And when I'm thinking about like two bedrock systems, I'm thinking about like the sediments in the bedrock that can potentially affect these hydrologic systems. And there's me. So first we went to, I guess second we went to a subglacial lake, but that's what I'll talk about first. And some of my driving questions here are, why do we have active subglacial lakes? Is our ISAT outline of lakes correct? How much water is in these lakes? And then my last two questions are, what are the water sources and where's the water stored? Which are sort of interconnected. I think sometimes we think about water in lakes as being basally sourced, but there is probably a groundwater component as well, so I'm interested in exploring that regime. And moving down to the grounding zone, I am interested in looking at how hydrologic systems interact with the ocean. So how are ocean and basal meltwater interacting at grounding zones, and sort of tied to that, what is the upstream limit of ocean water getting in under the grounding zone? And to do this, I use magnetotelluric methods. This is an electromagnetic method. And this schematic shows two different types of electromagnetic methods. On the left, I have what I call controlled source electromagnetic methods. And basically, we put a large loop of wire on the ground, and this loop generates an electromagnetic field which penetrates through the ice and induces secondary fields in the subsurface based on conductivity variations. So lakes, sediments, and bedrock all have distinct electrical signatures, so that's a good thing for us. And we measure those primary and secondary fields. So for those familiar with SkyTem, this is like SkyTem on the ground. This is very cool, but I'm actually going to talk about magnetotellurics, which are governed by the same physics, but instead of creating our own electromagnetic field, we use the Earth's naturally occurring fields as our source. So the same things happen. The Earth's field generates currents within the subsurface, both electric and magnetic, and we can pick up on those currents, and it tells us something about the subsurface. So this is what a magnetotelluric station looks like in the field. We have 4 electrodes and 3 magnetometers. We plug them all into the middle hub station, and we're just measuring electric and magnetic fields, which look like this. And this is just 7 minutes of our data. And what we do with these wiggles is we apply some physics, we apply Maxwell's equations, and first we develop a response function, which I will show next. So this is a magnetotelluric response function in a simple 1D case. On the y-axis, we have resistivity, where the top part is electrically resistive and the bottom part is electrically conductive. And on the x-axis, we have frequency, but it's flipped, so it's actually decreasing as we move from left to right. And frequency somewhat corresponds with depth. So as you have higher frequencies, it's shallower depths within the subsurface, and lower frequencies correspond to deeper surfaces, subsurface. So here in this plot, we have a few examples of what apparent resistivity curves look like. The blue line represents if we just have this 1D model of very resistive ice over basement, but if we introduce a layer of wet sediments that's 10 meters thick and conductive, we get a slightly different response. And then getting even thicker to 100 meters or 1,000 meters, we get a very different response. So this is sort of a nice check that our methods are sensitive to sediment thickness variations. And here's an additional synthetic test. So if we build a 2D model where blue is resistive basement, green is a more conductive sediments, and this red zone is a subglacial lake, which is a little bit more conductive. And we get response functions all along this profile and do an inversion, we can get an image that looks like this. So we can see we are sensitive to the presence of the lake, the presence of bedrock, and varying sediment thickness. So we're back at the Willen's ice plain where we actually collected magnetotelluric data. We went to Willen's subglacial lake where there has been a lot of geophysics already done and direct sampling from Wizard. And we also went to the grounding zone site for Wizard as well. So I will start with Willen's subglacial lake. We know that this is an active lake, so here's our relative height anomalies for the last 9 years. We can see the general trend over the lake is an increase in elevation, and we've gone through a couple of fill drain cycles in the last 9 years. The other activity that has occurred is geophysics, so seismic and radar data were collected in the 2010-2011 season, I believe. Yes. And then in 2013, the Wizard project directly accessed the lake, so we have samples of the water and sediments. And 6 years later, we collected our MT survey. So this is, I think, good to keep in mind that we are taking a snapshot of a system that is evolving. So this was the survey that we ended up collecting, where the triangles represent our magnetotelluric stations. We have the ISAT lake outline, a predicted flow path, and the seismic lines are in pink, so that was sort of the backbone of our survey. And I've also included where seismic data interpreted the presence of a water column, which you can see doesn't agree with ISAT very well. So that was an interesting thing we were trying to look at. We collected 27 stations in 13 days, and this kind of ratio of stations to days depends on wind. If that didn't, okay. So here I have wind matters. While we were collecting our data set, we also collected wind measurements, and basically here, the pink and green wind speed, so less than 8 knots is what we needed for our survey in order for our stuff to work. So I will pull out one station that sort of highlights this. This is an electric field spectrogram, and this time during low wind periods, we get responses that we would generally expect. So we have frequency and time on this axis, and this is our power for electric field spectrogram. But then as the wind picks up, we get these spikes that totally blow out our electric fields and render our data useless during those times. But from this, I would pick 10 hours of data, which is more than enough to process up some response functions. So here are some responses from Lake Willen's. And the darker purple sites are over the lake, and within the response function look pretty similar, which is promising that all of our on-lake sites look similar. As we get to the lake edge, we see, it's kind of hard to see on here, but there is this slightly different response. And as we're totally off the lake, we get a very different response at all frequencies. So this tells us there's something fundamentally different about our off-lake sites. And I'll quickly show the grounding zone responses as well. The darker colors are what we think are grounded sites, and the lighter blue colors are floating sites. So this black line is our grounding zone. And we can see again there is a fundamental difference between the floating sites and the and the grounded sites, which is what we would expect. And additionally, the conductivity checks out. So seawater is more conductive than freshwater, and that is what we're seeing here. The light blue floating sites look more conductive than the grounded ones. And our bonus site was Lake Mercer from the Salsa project, which looks totally different from our other sites, which I think is super interesting. And I guess for me, that means we should collect more magnetotelluric data on the Willen's ice plain so that we can get an idea of the regional variations. So we completed the first magnetotelluric survey of an active subglacial hydrologic system. Our magnetotelluric data worked both theoretically and in practice, and I'll hopefully have some 2D, 3D inversions at AGU. Thanks.
Chloe. As we transition, one quick question. Okay, we'll save it for the discussion. So for our last talk of this session, it will be Slawek Tulaczyk telling us about another active, well this time an active electromagnetic method in the Transantarctics.
Thank you. Yeah, thanks for sticking around. It's just one more presentation between you and the rest, so bear with me. The real title should be this: what sensor to turn to when your radar is lying to you. So that's what I'm going to be talking to a bunch of our collaborators from Denmark and other places that make this all possible. And well, the tool is really great. The electromagnetic tool is really great for looking for water. And water is very important. It's the gold of polar regions and planetary science. And that's because water, to find life, you follow water. And it's this slippery stuff that makes sliding possible and makes ice deformable, and it dissolves geology, makes nutrients, and feeds the coastal ocean. It erodes the continent, transports sediments to the edges, dumps in, so that all these people can be happy when they study it. And for now, radar is the main tool we're using to find wet spots in Antarctica. And it's used as a water detector through the ice sheet. Basically, strong, bright radar reflection from the base means wet, according to typical interpretations, and then weak basal reflection means dry or frozen. So I'll start with an example of from Taylor Glacier, where we can compare past radar studies and TEM studies that we did, and I'll tell you that we'll find a lot of water, whereas the radar studies did not. And there's been interest in finding liquid water beneath Taylor Glacier, mostly because of the presence of the only place in Antarctica where subglacial water actually doesn't take millions of dollars to get, but comes to the surface and begs to be studied. So there's the Blood Falls right there. So that hints at the idea that there's water beneath Taylor Glacier. And just for context, Taylor Glacier is this outlet glacier of the East Antarctic ice sheet. So McMurdo Station is somewhere there. And it's nice because it terminates on land rather than other outlet glaciers of this ice sheet that tend to flow into the ocean. And then it's hard to study their termini. Okay, so reviewing these two past studies, there was a surface radar work by Hubbard, this should be 2000, and basically dragged radar all over the lower part of Taylor Glacier and found mostly low reflection coefficient, which is this line, kind of dotted line. This is the shape of the bed from radar. This is the surface. And then only in some places there was a kind of a spike in bed reflectivity, which was interpreted as localized ponding of water beneath Taylor Glacier, but not a continuous water system underneath. And then a much more fancy system flown on a twin otter, and a paper by Jack Holt and colleagues basically says, well, it's complicated. And basically nothing about anything being wet beneath the glacier, but mostly complaining that there's sidewalls in mountain glaciers that reflect the radar, and there's a bunch of clatter because the surface doesn't look smooth. So where is liquid water beneath Taylor Glacier? Really? Everywhere. So this is a line that covers about 6.5 kilometers from the front of the glacier, flown with the helicopter-borne EM sensor. This one is 2018 line with cross lines from the 2011 survey, which kind of went back and forth across the glacier valley. And they basically show this channel of low resistivity, and it's maybe 100 meters thick or so. We interpret that as the brine-saturated sediments. The bluish colors, resistivity of about 10 to 100 ohm meters, pretty low. Glacier ice, in contrast, is pretty high, 1,000 to 10,000 ohm meters. And then underneath we have a signature or signal from transitioning to something a bit more resistive than these bluish veins, probably interpreted by us as brine-saturated bedrock, 100 to 1,000 ohm meters in greenish colors. So why does it matter? I'll give you an example. Let's say Jeff Severinhouse has his rate drill ready to go and wants to take it to Taylor Glacier. The rate drill is not a clean drill, So he asks his radar friends to radar Taylor Glacier, tell him whether the bed of Taylor Glacier is dry or wet. And they come back and say it's dry. So you drill, and because RAID uses borehole fluid, you contaminate this ASPA that's been designated as a protected area, and you violate the Subglacial Aquatic Environment Protection Act, or whatever that is. So, just an example, random example. Okay, my job here is to, pitch the airborne EM, so I'm doing that. Okay, so to see subglacial water everywhere, you have to use an EM tool because radar has a big Achilles heel, and that's conductive layers. Radar is awesome in air, empty space, and really, really cold glacier ice. They all have very little conductivity, electrical conductivity, so there's very little attenuation. You can see through that stuff very easily. But as soon as there's something real, like geologic, wet, that has conductivity, radar just gives up and dissipates away. So you want to use EM technique, which is not as pretty because it doesn't give you high resolution images. It's a diffusive technique. It still uses electromagnetic waves, but it looks at the rate of diffusion of energy into the subsurface rather than it's governed by diffusion equation rather than by a wave equation, as it is in the case of radar. And here is kind of what it takes in terms of hardware. Just like we've seen in the previous presentation, you need a cable loop supported in this case by a framework, and then you fly that around and ping every some fraction of a second to get data. You have a generator hanging up there, and a transmitter, receiver. You want to know your altitude about surface and tilt and all that to correct. So it's all on the antenna. I don't know how many of these sensors exist in the world, but probably not that many, like less than 10. And they've been developed over time mostly because of mining reasons, looking for conductive mineral ore deposits. And then in the last few decades, they're being used, including in the US, to look for aquifers and assess how much actually water there is in an aquifer for us to withdraw and grow crops. So if you really want to kind of find out about the technique and its applicability to polar regions, Neil Foley has a paper in geophysics that goes over this technique. This is a figure from his paper, which shows the raw data, which is basically the dB/dt, which is the rate of decay of the magnetic field, plotted as a function of time. And then you take a fancy equation and use inverse techniques to convert this kind of data into a profile of resistivity with depth, where time is a proxy for depth. Electrical resistivity depends basically in most geologic materials on porosity, so how much liquid you can store there, and also on the actual electrical conductivity of the liquid, so salinity of the liquid. And this is just a figure similar to the ones we've seen already about the induction of a primary magnetic field and then secondary currents in the subsurface and a secondary magnetic field, and that's what you actually detect. Okay, so just a few pretty pictures to follow the Taylor Glacier. When you fly over Ferrar Glacier, which is next door, you see also that there's a lot of conductive stuff beneath grounded ice. When you fly over Mackay, which was kind of at the maximum range of our helicopters, you also see that the high resistivity glacier ice sits on low resistivity saturated sediments, except, the point here is that when we fly over smaller glaciers that are not outlet glaciers of the ice sheet, we don't see that. There is no low resistivity liquid stuff. Okay, and then finally, the other thing that we see glaciologically significant in our data is that actually there is appears to be lower resistivity of glacier ice close to glacier termini in the parts of the glaciers that are actually in summer melting on the surface. So my working hypothesis right now is that water infiltrates into fractures and winter freezing warms up the ice column, and basically ice resistivity depends on the same parameters as ice viscosity, so temperature, water content, solid content. So these lower parts of the glaciers are already feeling kind of warming and melting that's impacting their internal structure. This is just a map showing the flight lines from proof of concept study in 2011 in cyan, and then some ground-based surveys we've done in 2017 and black surveys in 2018. And then, oh, did I forget to mention that Neil will have, oh no, that's on my conclusion slide, I hope. Yeah, sure. What's TM good for? Well, looking underneath ice. So radar gets to the bed, it's all pretty and layered and amazing, and then it stops at the bed when there is something conductive. And you don't see the stuff underneath, and you need to use this to see the stuff underneath. And then good luck doing active source seismic from helicopter or plane. I would like to see that. And then we can also map saline or perhaps also weak parts of ice shelves, and that's where my pitch for Neil's presentation tomorrow comes. 11:45. Be here on Friday. There's going to be carbonated beverages, I'm sure. Okay, mapping out temperature and viscosity structure of glaciers and ice sheets, and then we should kind of try to pull this method in to add to the geophysical toolkit that we have, which is right now radar and seismic. And that's it.
Thanks, Slawek. And as a radioglaciologist, I've decided there are no questions for Slawek. If everyone who's I lie to myself all the time. If anyone, if the speakers could come up and join the panel, and while they're doing that, quick questions for Slawek. Yeah.
What kind of ice thicknesses and sediment thicknesses can you see with TEM?
That's a good question. So from the airborne, we were able to see through about up to 600 meters of ice. And the ground-based version of it, since we can sit there and stack the signal for a while, gets us through about 800 meters of ice. And then what kind of thicknesses of stuff underneath depends largely on how conductive it is. If it's very conductive, we also lose signal. But if it's not very conductive, you could see that we can see like 100, 150 meters of sediments.
Could we ask the same question to Chloe for MT?
Yes.
So with magnetotellurics, you can see a lot deeper. The resolution is not as great as SkyTEM, but people have used magnetotellurics on ice sheets and elsewhere throughout the world, and if you leave your stations out for long enough, you are looking at mantle structure. So the depth range is really huge for magnetotellurics, but for my project, we left our stations out for maybe 24 hours, and that's plenty to image like several kilometers depth.
I completely agree radar lies a lot, but are you able to distinguish from the Taylor Glacier case between the aquifer going right to the bed of the glacier versus being underneath a layer of frozen till maybe?
Yeah, so there's definitely a basal ice layer at the bottom of Taylor Glacier. The method is, maybe Neil can chime in, but I don't think it has high resolution enough vertically to distinguish between something that's like 10, 20 meters thick. It's just too diffuse. So we just see the thicker layers.
I have a follow-on question with that, actually. I mean, one of the things that we try and do with radar to calibrate for water is find a known surface, because often we're looking at relative reflectivity, not absolute. And so can you confidently interpret anything as an interface property instead of just a body property, kind of just as Duncan asked? I mean, you seem to find that at the lake, you could see a difference in water content, even though it's certainly water saturated till around subglacial equivalents. It would be nice if there was a complementary method to say there is water at that interface, and then use that to calibrate radar observations collected coincidentally. Do you think that's at all possible with either method?
I'm slightly confused by the question. So, is there water?
Well, so I think of electromagnetic methods like you described as body properties, and radar is an interface measurement tool. And so we can't measure deeper into the sediment and see if there's water or basal ice or some other property. So if you could use electromagnetic measurements to calibrate radar data, it seems like that could be a powerful combination. Do you see potential for that at all?
Yeah, I see that as being a very powerful and like something tool and something we should do. Because especially, like I guess from my perspective, I can use like radar reflections to say there is an interface, like some sort of stratigraphic interface that I can then use to like constrain an inversion, which helps give me a better image and like nail down conductivity or water structure better, so that in turn I think would then inform radar better as well.
I agree.
Nick, we showed that in this.
Basically, you could benefit from radar data. Going the other way, I think we would have to nobody has ever had a study, from it. We would have to spend some time thinking about it, how EM results can benefit radar.
They're joining in the groundwater community. They're starting to have joint inversions that are doing the fusion and the wave equation simultaneously. Sorry, that was nerdy.
Just quick remark. Neil was able to see the dusty ice from the glacial period on Taylor Glacier, as opposed to the clean Holocene ice. Is he here?
In the back, yeah.
Oh, okay, yeah.
What did I say?
I think there's definitely, just like that slide said, glacier ice resistivity does change with temperature, with water content, and with impurity content. So it's quite possible. The slides I showed you were mostly kind of focused on displaying the low resistivity range, the stuff that we see beneath the glacier. But one of them had that display at the high resistivity range, and then we start seeing variability within the ice itself. No, are you answering anything, Neil, or are you just dodging?
I didn't quite catch the question.
Oh, I didn't quite catch the question.
Okay, so Jeff will talk to you separately.
Okay. There were also direct measurements, biology, radio, isotopes, lots of things to be interested in.
I have a question for Grace. So, what's the significance of having the precursory phase? How does it change the picture?
What do you mean? Like, what is the significance for what? Like, for the stick-slip cycle, or?
Well, in general, for how stick-slip cycle works, how failure works. Explain to me. How would you motivate study?
Yeah. Well, so the Willows Ice Plain, the stick-slip cycle is like actually one of the most easily observed earthquakes in the world. On some level, it's like kind of a slow earthquake, but it's an earthquake nonetheless. It's an unstable slip event. So actually being able to see a little bit of precursory movement and how it relates to the main rupture is actually a very special kind of observation. Yeah. Being able to kind of like see what stress regime it is in which those kinds of things happen before a slow earthquake is pretty special.
Question for Eliza. So you kicked the session off, and then there were two talks at the end that talked about how we can identify potentially frozen versus thawed. How quick? So your models were just instant transition from frozen to thaw. Is that how we think it'll work? In which case, time-lapse geophysics could work, or is this a slower process? In which case, we can't leave an instrument out for a century while it thaws. I'm just thinking, as an observationalist, what I can do for you.
Yeah, that's a good question. So for my preliminary results, I was just modeling this as a step change. But I really think that this is more like a propagating front, and that over time it's going to evolve and move up like the catchment and further interior. And so I think that for isolating where these subtemperate regions are and trying to get a better constraints on where these thermal propagations could kind of initiate could be a role that some of these geophysical techniques could really play a key role in. And then I think that could be kind of motivation to then keep on looking at this propagation and how this friend moves. And mine was kind of like a first attempt to try to include this more complex theoretical wave propagation in a parameterized sense in a larger scale ice sheet model.
I have a question for the EM techniques. Are you assuming that the content of your lake is just pure fresh water? And do you always make that assumption? Or
so the nice thing about my surveys is that we have direct sampling from Wizard, so we know that it's fresh, but there is like a slight seawater component, like a few percent. So that's actually very useful for me as I start running inversions, that I can constrain the conductivity of the lake to help better constrain the rest of the model as well. Like it's just one more known that you can throw in. But yeah, for other lakes, it would take some more thought. But on our Mercer site as well, we have direct measurements, so that's useful.
and for the TM as well?
To get back to activity.
Good question. Like, let's see. I don't have a lake, so how should I read this?
Oh, okay.
Yeah, but we do. You know, you can do modeling using something called Archie's law, that comes from oil industry. It's an empirical relationship, or that basically expresses the bulk resistivity of the sediment as a function of porosity and fluid salinity or resistivity. So we can do some modeling, and that's why. One reason why I called these sediments brine-saturated sediments, not water-saturated sediments, is because, it looks like they're really low resistivity, and it's consistent with the type of brine, very hypersaline brine coming out of black holes, being also in these pore spaces.
This is for Chloe. I was going to ask you it later, but I may as well ask it now. Towards the end, one of your last slides, you showed that Mercer is significantly different than the grounding zone and Willans. And I'm not asking why or how for you to explain that difference, but can you just explain that figure one more time? What was that conductivity that was different, and kind of Mercer was doing its own thing?
So apparent resistivity curves are sort of weird to look at. It's like if you were to collapse all of the conductivity variations that you have beneath you into like a 1D type model, the response that you would get, it's sort of a weird way to think about it. But basically on the y-axis it is resistivity or conductivity, and Mercer looks a lot more resistive, which checks out with what you guys observed when you sampled the lake itself and the sediments beneath. I think this is mentioned at least on the posters and probably in the salsa talks that we heard, but the water in Lake Mercer is a lot more resistive than Willans, so that sort of acts to shift that curve up, and I think there's probably some deeper geology as well that acts to shift it as well.
So I don't really know much about interpreting the chemistry of these subglacial lakes, and in this case, some or much of it is trapped marine material. But is there any utility in knowing what the upstream, like mapping using these geophysical methods to characterize the upstream parts of the hydrologic system to know what's feeding into it now that it's trapped subglacially, or is that not helpful?
I think it definitely is. For instance, I really like the bullet point in Slawek's talk where he said that water can dissolve geology, right? And that provides a lot of the chemical energy, the substrate that these systems can work on. One thing that I forgot to mention when I mentioned that the results I presented look like, it doesn't look like the tail is wagging the dog. It's really hard for us to test whether the dog is wagging the tail using the same radioisotope methods because the sample sizes of biota, we don't have amphipods to measure. We have those tiny little dots in that slide that I showed. Right? We just can't get enough of those to measure. But Christina Davis and Ryan have they're doing sort of a pilot study to figure out if we can measure the EPS, which is the extracellular polymeric substance, and basically it's microbe snot. Hopefully we can get enough of that to measure and see if that does have the signature of the DIC, which would be then older than the sediment. And in that case, you can kind of argue that what's coming from upstream and what exact geology is dissolving is important to these systems.
But then you're going to try and get the creepy crawler bits that will pull out of Mercer, right?
Yeah, that's true too. Yeah, the relatively fresh, more advanced skeletal parts that we found. Hopefully, we can get enough of those to date as well.
So both Chloe and Slawek kind of touched on there being a lot of sediment beneath the West Antarctic ice sheet. Can you guys discuss the implications of this new knowledge? I mean, in the past, we've only known that there are a couple of meters maybe of sediment. So what does it mean for the ice sheet if there's more sediment there than we knew before?
I'll try. I'm fairly new to glaciology.
Long time
But-
listener, first time caller.
But I mean, I like how I think about it. If there's more sediments, I mean, maybe Eliza, you would have an answer to this. If you have more sediments that you can deform as like a glacier is sliding across, I would imagine it affects how we actually think about flow across these glaciers, and if they're like water saturated, that could affect these like soft regimes that you can flow over versus like harder bedrock regimes. Yeah.
Well, I mean, since Richard Alley was talking about this layer of forming till, we've known that there's this sort of mobile mixed water saturated stuff. We've never penetrated it in all of the coring that's been done through the ice, but we also know underneath that is plenty of strata. Certainly, maybe not in all the bedrock highs, but in all the valleys, they're all sediment filled with hundreds and hundreds of meters of sediment. That's just a matter of how lithified it is. But there's the stuff that's all been mixed up by glaciers multiple times. It's not just we tend to sort of think about the last glacial cycle, but it's happened lots of times that it's you're constantly eroding the layers underneath and incorporating them into this active till, and so it's a whole lot of complicated stuff. And yeah, Slawek, I was going to say, Slawek can talk about the rheology of this stuff and the permeability.
You just read my papers and cite moved on. So I actually want to take that question and deflect it by turning into a question to Eliza, because like the system that we see, we see sediments with water in it, liquid water in it, but the base of the glacier is like at -8, -6, So how does that translate? When you calculate or you estimate what's frozen, what's melted, how would you deal with zones where in theory the water should be frozen, but in reality it's not because there's a lot of solids in it?
I think that's a great question. I don't have a great answer. I think that is a really important component of understanding these thermal transitions. And right now, I've mostly been doing fairly simplified experiments where I'm not really looking at all the subglacial hydrology, but that's definitely a component that I want to look at in the future. And I think that piecing apart where these subtemperate regions are and where we're getting the deformation and exactly at what region do we start to really see an onset of sliding is where understanding what the subglacial geology is will really come into play. So would like to work on it more in the future.
Going back to the previous question about what's the importance of those thick sediment packages, it occurs to me that one of the differences might be the way that groundwater interacts with the ice sheet, in the presence of crystalline bedrock versus over consolidated sediments and actual sedimentary rock. It's not something we talk about a ton. We do talk about it occasionally, but it might be, kind of an important thing to think about.
Yeah, on the topic of groundwater, I don't know if I actually highlighted this in my talk, but we are hoping to see deeper groundwater systems with our EM results. So some of the pore water analysis from Willen subglacial lake indicate that there's probably a deeper saline water body, I guess, in the sediments at depth. So that's something we're hoping to see and maybe come up with some idea about how, these deeper groundwater reservoirs might be interacting with these more basal hydraulic features.
This isn't really something any of you talked about, so maybe more of a discussion question, but Martin had a nice poster yesterday about basal melt channels on ice shelves, and he suggested that those might be initiated by basal melt coming from the ice sheet. And I was sort of curious if any of you had any insight into that, like Eliza, for example, if the onset of more sort of warm-based thermal regimes is part of that, or the draining of subglacial lakes, which could then mean that actually groundwater is part of it. So just any insight you guys have into those processes.
Yeah, that's not really something I've looked into yet, but could definitely be interesting. I've been trying to focus more a little more interior and not looking right at the cavern front because there's all these other complications that come in there. And so it's really hard to kind of piece together where that exact mechanism is derived from. And there's also, with basal melt, there's the Niagara all the ocean forcing at the cavern front too. So I think it's interesting, but I haven't looked into it yet.
So this is for Chloe. I'm impressed with the inversion that comes out of your group that you've done and others in your group have done. I was wondering if you could talk a little bit about what the limits on it are. Perhaps what's the smallest contrast in resistivity that's resolvable? What's the thinnest layer? What if there's a gradual transition of resistivity? Does that affect your inversion?
Those are all really good questions. We need somewhat significant electrically conductive contrast. In the synthetic 2D example I showed, I think the sediments were maybe an order of magnitude different than the bedrock electrically, and then the lake was, I think, another order of magnitude. So you do need these big contrasts. I wouldn't be able to tell you the difference between something that was 10 ohm meters and 20 ohm meters. It kind of does get smeared out. And as far as the spatial resolution, it's more on the order of tens of meters, whereas if you use SkyTem, I would say it's more 5 meter resolution-ish. 10? Okay.
Decreases with depth.
Yeah. And with depth, your resolution also gets slightly worse.
What about if you've got a gradual transition? Is that something you can detect, or does that sort of show up as ambiguously a sharp transition at different points? Or
for our group's previous electromagnetic work, we have been able to sort of capture these sort of transitions, but our inversions are inherently non-unique, and in the EM world, if you have a very thin conductor versus a medium-sized conductor with that's slightly less conductive, but they have the same conductance. Conductance is sort of similar to mass, I guess. So if you had a really small dense ball versus a larger ball with less density, but they have the same mass, that sort of plays out in EM methods where you can have these somewhat equivalent features, and they can be hard to resolve. But the cool thing about our data set is we do have all this extra geophysical data. There's radar, there's seismic, there's direct sampling, and this was sort of the motivation behind doing our survey where we did it, is because we have all this extra data to sort of help narrow down our models.
Why don't we make this the last question? Maybe something that links all the talks. Maybe
No pressure.
Go ahead.
I didn't know if you were gonna cut me off.
So my question is for Chloe. I hope I'm not bursting anyone's bubble here, but all of you know that simulations crash all the time, and you have several different ice sheet models, and they have all these differences that pop up, and sometimes they don't work at all. So one of the questions I had is, you have this motivation for frozen to sort of slip type or sliding type condition. Is there any motivation on the modeler's end to put this criterion to stop any convergence issues, or does that lead to a better stable simulation run, or is it all about the physics in your study?
I think, did you mean me? I'm pretty sure you
Eliza, for Eliza.
Oh, sorry, Eliza. Yeah, sorry.
Dodged a bullet.
So there's many different ways you can go about trying to kind of capture this sort of propagation. And right now, what I'm really looking at is just how can we implement the change in basal friction in regions that are very close to melting. And down the line, I am going to be running a lot more simulations and doing a much more robust analysis of it, and potentially look at incorporating temperature into sliding laws. But right now, it's really just a forward model where I adjust my friction, so basically just allowing the bed to be more slippery and just allow the model to evolve in that way.
Okay, one last question.
Can I just add one thing on this one?
If it's field change.
I just want to add
one thing on this point that he raised, and that is besides the interest in the physics there is one fundamental reason behind looking at how this temperature-dependent friction works. The problem is this work that is coming out right now by me and Christian Schuf, that if you actually do a hard switch between non-sliding and sliding, and you refine your grid well enough to look at what happens there, you'll find out that that problem has no solution. So it's not the problem of a singularity, it's the problem that you're going to freeze again. So your bed is not going to be able to remain at the melting point. So the continuum model that is underlying basically every ice sheet model that is around has no solution. And so that is the reason behind this work, really.
All right, why don't we thank our subglacial observers one more time?